One final function to look at is the rot function. Rot is really a convenience function that saves you from having to calculate sines and cosines to determine how to rotate a particle about a given point. You're looking at a good example of the rot function that moves particles, which have been emitted from a curve, around their emission points on that curve, similar to the way the dust particles would swing around a tornado. If we look at the creation expression, we can start to break down the steps required to contribute to the rot function. Since the particles are being emitted from a curve, and the emitter is giving the particles speed based on the curve normal, we can capture the normalized vector of the particle's direction and use it later. Since I only want my particles rotating about the y-axis, I've captured the vector into a variable and used only its y component for a per-particle vector attribute called normal pp. We also have a per-particle vector attribute called pivot pp, which will store the particle's point of emission. Note that we have to capture this position before we offset the particle. Finally, we slide the particle out in space, again using the unit function to determine which direction to move the particle. We then multiply this vector by randomizing it with two attributes on the particle shape called min-dist and max-dist. Then we simply add this vector to the particle's position. Next, we start work on the runtime expression. Because the rot only takes rotation amounts in radians, and it's generally easier to work in degrees, we have to convert our angular units. I've created an attribute on the particle shape called rot speed, which I've set to 10. To perform the conversion, I'm using deg to rad, which returns a float. We have to calculate the particle's position about the origin as the rot function rotates about a default pivot of 0, 0, 0. Next, we calculate the actual rotation and push the result into a vector. Finally, we apply the rotation to the particle, but through the particle's velocity. We could drive the position of the particle directly, but it's better to assign the rotation to the velocity so that the particles can continue to be influenced by forces. I've added another attribute to my particle shape called rot force, and I've set it to 10. Rot force is a multiplier to the resulting velocity vector, which is determined by taking the particle's old position away from the newly rotated position. This moves the particle in a circular fashion around its pivot point on the curve. To modify this simulation to look like a tornado, I would simply add a buoyancy factor in the form of a per-particle float and add that random value to the particle's y position. I could also decrease the particle's distance from the curve, depending on how high off the ground plane it is. Another interesting thing that can be done to this runtime expression is to not flatten the normalized vectors of the particle's velocity. Because the curve emitters emit particles in random directions, we can use this direction to determine the plane about which the particle rotates. This file has slight modifications made to our original creation expression. I've also animated the curve a bit using the wire tool. Here, we have the option of specifying whether to flatten the plane of rotation or to use all three axes. We have control over this with the eddy attribute I've added to my particle shape. We call this attribute eddy as setting it to on gives the particle cloud small swirly pockets of greater motion, almost like the inside of a smoke cloud.